Hi, this is a presentation to summarize the work done by Team Pentagon from Ericsson in the ITU AI/ML Challenge Track 18 Compression of Deep Learning Models. The contributors of this work on multi-context based knowledge distillation are as follows. Here's a little bit of background of the problem statement. Recent years have experienced an unparalleled development in information, communication, and technology. This sector has gone a long way from 2G communication to 5G communication. With the advent of 5G, the number of applications that require edge-level computing, like autonomous driving, augmented reality, and other hard time-constrained tasks, are flourishing. While deep learning model proved to be very successful and very appealing with its results, they come at the cost of size and complexity. Here are some of the challenges. It requires millions of parameters, it demands very high computation power, and it is too large to be deployed on an edge device, and it is very difficult to be operated in real time, and it's large latency. So to address this issue, we studied different deep learning model compression techniques and found the following prior arts. Model pruning is an optimization technique that involves eliminating unnecessary values in the weight tensor. Though it is capable of compressing models to a great extent, it is very difficult to train from scratch, and it suffers some loss of accuracy when pruned to a greater extent. Another challenge is that it is very difficult to generalize. Model quantization is yet another technique which works by reducing the number of bits that represent a number. But this technique reduces much of the memory occupied but not the computation, as it loses information in the process. Knowledge distillation is another technique to transfer information from one network to another whilst training it constructively. We chose knowledge distillation as our approach, and we tried to overcome these two challenges, which are the teacher can't effectively distill its knowledge to students for all the data distribution, and not much of insight is available about the best student-teacher combination. We also found other frameworks like TF-Lite that perform computation on edge devices, but they have some hardware constraints. For example, TF-Lite is optimized to run inference on ARM CPU edge devices, but it does not have efficient support for Intel CPUs and NVIDIA GPUs. From the initial experiments, we found that a teacher cannot distill all its knowledge to any kind of a data distribution. By this, what I mean is, even though the teacher is trained on a lot of data and it can generalize well on any input, the student cannot perform well on all image data. Each and every model architecture works well on different kinds of data. This motivated us to develop a context-aware knowledge distillation method, and to the best of our knowledge, we are the first to address the problem with a multi-student architecture.
The dataset we are using to perform all our evaluation is Cypher 10 dataset, which consists of approximately 60,000 images of 32 into 32 size, and it's an RGB image where we have approximately 6,000 images per class. So here we are using an Google Colab to train, so which has an NVIDIA P100 and a RAM of 16 GB. And the most important libraries that we would be requiring is CUDA, CUDNN, PyTorch, and we use Python 3 to perform all this, and Torch Vision is used in this calculations. The traditional student-teacher pipeline has a teacher model that effectively distills the knowledge to a given student model. But in our initial observations, we find a problem with this pipeline. A given student model cannot work well in all kinds of data geometry. So here we propose a novel architecture called a multi-student knowledge distillation model. So in this, what we say is we take a teacher model, we effectively distill the knowledge to two different student models which have a completely different architecture, and here we optimize the distillation loss, which is basically the knowledge distillation loss plus the binary cross entropy loss, which is taken from the between the predictions and the actual labels. After optimizing this, we have a two completely trained student network which can form a hyper decent inference on a given data, and the fully trained student network. Once we have this, we take these student models, the trained student models, and perform predictions on a given set of data. These predictions are actually compared, both the student models performed a prediction. These predictions are actually compared with the ground truth. The Euclidean distance, which is basically the absolute error between the ground truth and the predictions performed by both the models, are calculated. Basically, the predictions is nothing but the class probability of a given image data. Once we have this absolute error between the ground truth and the predictions of both the student models, we see which student model is performing better on a given set of input data. So for the corresponding data, we form a mapping table as to, for a given data, which student model is performing better. Once we have that data, we take that as the input. Basically, the input is nothing but a given image and the output is nothing but the the model which works better, like student 1 or student 2. Once we have that, we train that as an input and output data using a highly compressed network, highly compressed 3-layer CNN network as a model selector. So this model selector will be able to understand this mapping. This is a final standalone architecture where we perform the inference on this. The previous one was this training. This is the inference one. So here we take, after completely training the model selector, what we do is we just give an input data. Since the world is moving towards an active learning, we can get any kind of an input data. We give the input data to the model selector. The model selector understands what kind of a data it is, like it extracts the high level attributes from the data, and it estimates which student model can perform a better inference on that, which can infer the class probabilities much better. So it routes the given input data to that model, which is basically the model selector is performing a routing operation, a comparator operation over here. Here we have the meta architectures of the models we used. So the teacher model was a pre-trained ResNet 50 model which has 50 layers, and the student model 1 and student model 2, which are nothing but the DenseNet 121 and GoogleNet models. Here we have the model attributes. So the teacher model is a ResNet 50 model with 25.6 million parameters and 98 MB as the parameter size, and it has 50 layers. The student model 1 was DenseNet 121 with 3.27 million parameters and 31 MB as the parameter size, and it has 11 layers. The student 2 was a GoogleNet model which has around 6.07 million parameters and 25 MB as the parameter size, and it has 22 layers. The model selector, which is a custom defined CNN 3-layer architecture, which we'll discuss in the few further slides, it has around 50.05 million parameters and 2.21 MB as a parameter size, and it has 3 layers. So basically, to elaborate on the algorithm first trains so we go by the following workflow. We train the teacher model completely. Once we have a completely trained teacher model, we use the softmax output of the teacher to train both the student networks. Here we use the soft labels because we don't want the teacher to learn too much and the students to not learn pretty well. So we basically increase the temperature of the teacher model and use the soft labels to train both the student models. We optimize both the binary cross entropy loss and the knowledge distillation loss of the student models. Here we define a custom loss function basically, which takes the weighted average of both. And once we have the completely trained students, we use this we perform inference using both the student models. Basically, we run the student models to perform predictions as class probabilities for a given image data, and we see which student model performs better on which kind of image data. So once we have this mapping between a given data, like given image data, and which student model works better, like model 1 or 2, once we have this mapping table, we leverage this mapping table to train our model selector network. So once we have a completely trained model selector network, we then go to a standalone inference network, which is nothing but model selector and both the student models. So the model selector will take the input image data as the input. It will understand the attributes. It will route it to the according student model, which will basically form the conclusion, perform the operations or form the conclusions on the given input data. As we saw in the previous slides, the knowledge distillation architecture proposed by us was able to compress the model in all the possible parameters. The compression was pretty great. But are we compromising anything on the accuracy? So let's evaluate that. Here we present you the accuracies where we evaluated our model on the Cypher10 dataset. So here we find the accuracy class-wise. So here you could see that majority of the classes, like around 6 classes, the model selector, which is the proposed approach, is able to perform pretty well. On other places, there are two places where the student model 1 is winning, then two places where the student model 2 is winning. So this is one of the predominant reason why we chose these two student models, because they were kind of acting complement to each other. So that is one of the reason we chose these student models. So we see that we are not compromising anything on the accuracy. We are able to achieve up to like a maximum accuracy of 91% using the proposed approach, and an average accuracy of around 80% using the proposed approach, which is like and at the same time we are compressing the network to a great deal. Here we present you the results for the compression of the student models and the proposed approach, and the overall compression with respect to the teacher model. So basically we are analyzing the compression on three attributes. One is with respect to the number of parameters, that is on computing efficiency, and the space consumed, which is the memory footprint, and the same time MAC, which is the number of multiplication and addition count. So we find that the dense net is compressed up to 87.3% with respect to the teacher. So in this way we produce the compression results for all the models. So we find that DenseNet and GoogleNet are approximately 87.3% and 76.3%, and with respect to space consumed, it can reduce up to 67.4% space with respect to the original model in DenseNet 121, and GoogleNet it is 74.49%. And with respect to the number of MAC counts, so DenseNet is like not performing that great in that. It's around 20. It's just able to compress up to 20. It's just able to compress 21% with respect to the teacher, and GoogleNet is performing pretty well in that. It's around 68.1%. It's able to compress with respect to the teacher. With respect to our proposed approach, when we see that when we use the student model and the model selector in a series, we find that we have presented the results of number of parameters, compression with respect to the number of parameters, and compression with respect in considering the space consumed also. And interesting scenario might occur. What if the model selector fails? What if the data is fed to both the student models, or in some scenarios both the students have evaluate the same data, in some hypothetical case or in some exceptional case where the accuracy is same or something? In that case also our proposed approach can compress 61 up to 61.4% with respect to the teacher model, and with respect to the space consumed it can compress up to 40.61%. So our entire approach is pretty good, is what we would like to say here. An interesting question might occur, which was also asked by the organizers, like why did we choose the models what we choose? What is the reason behind selecting these models? Resonant 50, which is the teacher model, it was given by the competition organizers, so we chose that. And for the student models, we chose DenseNet 121 and GoogleNet. The first thing is because, as you saw in the slide 11, where we had presented the Cypher10 datasets accuracy on each class, the graph for that, we find that both the models were acting complementary to each other. Basically, if for example, if GoogleNet worked well in 5 models, DenseNet worked well in the remaining 5 models. So we are able to get an equal distribution of accuracy. The Gaussian curve was pretty perfect. So in that way, we chose these two. We chose DenseNet 121 and GoogleNet. And also the chosen model had very less number of parameters, which is just like 3 million and 6.07 million. And it provided very good accuracy, just the way the teacher did. And also an interesting question might come. The custom model selector that we used, which we mentioned in the initial slides, it is nothing but a 3-layer CNN. So the fundamental role of model selector is to choose a student which performs better on a given input data, basically estimate which student would perform better. So the role of model selector would be to extract the input data from the input image, and at the same time understand the model's features also, like which student model will work better. So it has to understand the student model's features also. So for this, it's like nothing but a model and data aware network. To perform this, which is like novelty in this approach, we first tried a 2-layer CNN with and without batch norm. It didn't work well, and a 3-layer CNN without batch norm didn't work well, but a 3-layer CNN with batch norm worked pretty well. But the moment we go to a 4-layer CNN without batch norm, it was overkill for the network, which is like learning unnecessary parameters, or like it is overfitting, which is not generalizing well. So we fixed 3-layer CNN. It is an empirical study we carried out to fix on this architecture. Here we present you the overall results. So the table that you are seeing on the top left, gives that the teacher has an average accuracy of 81% and the student has an average accuracy of 74.19%. Student 2 has an average accuracy of 73.1%, and the model selector plus both the student 1 and 2, which is like augmented one, has a combined accuracy of around 81.79%. So here we first thing we infer is that both the students model perform better when they are augmented with the model selector, which kind of reinforces that our approach is a very promising area of research to the future. And at the same time, we are able to achieve these accuracies even individually. The student models haven't compromised on the accuracy. At the same time, with when augmented with the model selector, also they didn't compromise on the accuracy. So they were able to get this good accuracy without compromising on the compression. Also, like it was able to we were able to achieve a huge margin of compression. A very important factor to be noted here: why teacher is not performing as good as model selector. That's because at least we hypothesize that the teacher is a highly over parameterized model. It has like lot of layers, lot of parameters, so it could potentially overlearn, or it could be overfitting, or it could be learning too much about the data which is not necessary to, which is not, or which might be additional information which might confuse the network while it's performing an inference on an unknown data. But the model selector, which has just what is necessary and which is like having optimum number of layers, it is able to learn only what is necessary and the important features, and it's able to perform a very good conclusion. So another thing that we observe is, why did we stop with 11 epochs or 12 epochs? We found that both the student models were like increasing as the number of accuracy of both the student models were increasing as the number of epochs were increasing. But as soon as we reach around 11 to 12 epochs, like 10 to 11, the accuracy started hitting a plateau. So we stopped there, and from there we continued our research. So as the number of epochs increases, so we have a trade-off also. So though the number of epochs increases, we don't get the linear increase in the accuracy. So this is with an empirical study we found this. Here we have represent the ML architecture for the training in the ITU format. So basically the simulated data, the data set which we obtain from the users, are being fed to SRC. SRC is nothing but the data source, and C is nothing but the collector. So the collector feeds the data to pre-processing operation, and the pre-processing operation sends it to the defined model. In our case is the teacher model, and the teacher model feeds the network to the policy, basically the heuristics or the machine learning hypothesis that could potentially perform the predictions. The prediction goes to the sink, and that output of the sink, which is basically the prediction of the class probabilities, are fed to both the student networks for training. So both the student networks gets trained in the same fashion, but here the output is nothing but the soft labels probability. Both the outputs of the students, after they are being trained, they are being fed in a sequential way to the model selector. So basically the model selector can indirectly understand the distribution between the input data and the corresponding student model that will perform better. So basically what is learning here is the model is also, model selector is able to understand, which is like a highly compressed model, is able to understand all the attributes of an image data. At the same time, it's able to understand the attributes, or it's able to understand the features of a given model. So it's able to learn, it's able to condition a given model on a given input data, which is a important contribution, or a notable finding from our research. Here we have the ML architecture for inferencing in the ITU format. So after completed training, here we have it for inferencing, where we get the real data from the service network, and that is fed to the model selector, so which is a standalone architecture. The model selector will perform the prediction as to which student model will work better, and accordingly route to the student model so that they can perform the prediction, they can calculate the predictions. Anyone who will have a question in their mind, who is watching this, like how are we going to integrate it with the 5G deployment? So since the way we already mentioned, 5G and edge computing are inseparable with the amount of edge devices and amount of computation data that's growing over time. So we see that both 5G and edge computing can act complementary to each other, where 5G can increase the amount of bandwidth and edge computing can reduce the latency. And 5G cannot work without edge computing. First, it's because of the inherent 5G standards, as it is the only way to meet the latency target which the 5G has set, which is less than 1 millisecond as network latency. Just improving the radio inference alone will not achieve these targets, so we need to bring in more machine learning and edge computing to work on this. So here we propose an architecture for doing the same. So we have multiple edge devices, as you can see, edge 1 and edge 2. The edge 1 and edge 2 takes the data from the input user, multiple edge devices, and it sends the data to the base station. The base station just sends it to the LAN layer. The LAN layer doesn't know to perform any inference or anything. It just takes the radio network layer, just takes the data, and it sends it to the core network. The core network will accordingly know which application layer the data has to be sent. This process will happen in the core network. The core network will send it to the application layer cloud. The application layer cloud will have our model selector on the student model network. This data will be like processed in the application cloud, and the application cloud will form the inference on this data. So like it will determine the class probabilities or regression problem, whatever the problem is. The application cloud will be able to give the appropriate outputs. The output or the inference basically will be fed back to the core network. The core network will feed it back to the RAN layer, and the RAN layer will feed it back to the base station. The base station will be able to accordingly route it to the mobile device, the edge device that actually needs the inference. So this can speed up the entire 5G pipeline process and can form better inferences. So in this way, our model architecture, how it comes handy here is that the edge devices can send any kind of a data. A single student model in the application cloud cannot handle all these variations of data. So we have multiple student models in the application cloud which are highly lightweight, and we have a model set which is lightweight that will be able to just take the input data and it'll say which student model will work better, and that student model will alone perform the inference and perform all the operations and send it back to the core network. With this, we save a lot of latency and we save a lot of space, and we will be able to save a lot of memory, and also we get a very good accuracy. Okay, so to conclude our work, we find that in this work, the initial experiments revealed that the underlying data geometry affects the model's prediction. So we just cannot have arbitrarily just one teacher and have one student and expect it to perform well in all kinds of data distribution, which is not happening. And the world is more moving towards, so this kind of tells us that knowledge distillation is not like the only solution or the universal solution to perform inference on all kinds of data. So since the world is moving towards active learning, like we do not know what kind of a data we will be getting in future. So we should be having multiple student models, or basically multiple compressed model on the edge devices on the application cloud, so that that can accommodate all the variations that could possibly occur to some extent. So this demands for a multi-student architecture. So that is what we have proposed here, a multi-student architecture which is like which has a highly compressed model selector. So basically this can accommodate at least like all the amount of variation, or like this can accommodate generally to maximum a good extent of variations that could occur in the incoming data, and route it to the model which will perform best in the least given time. So in this way, we optimize both the time taken and the computing power and the memory footprint, and at the same time we don't compromise on the accuracy. So to prove this hypothesis, we kind of tested all our results in the Cypher-10 dataset by carrying out extensive empirical study. So the proposed approach kind of reveals that the multi-context aware architecture performs better than the input student models, and in fact better than the teacher model also at times. So the observed results kind of demand a pressing need to understand the nuances. Like we need to understand why this is working, what this is working in depth to perform future research. And this shows a very promising area of 5G edge computing scenarios. And we believe that this can succeed as a general and a practical approach in near future. And though we have like performed some studies, we would like to take this as a future research work and perform the following. We would like to like try different number of student models. Like right now we just have 2 student models. We would like to see, to accommodate all the possible variations, what is the least number of student model that we could use. Is it like 3, 4, or like we would like to explore that, keeping it as an optimization problem. And we would like to try to like simplify the student architecture further. Like can we just have a 4-layer CNN, 5-layer CNN or something like that? We would like to evaluate our results on that. And at the same time, we would like to check for cross-modality dataset. Like right now we are using image dataset, but what if a text dataset comes? How can we do it for BERT? How can we do it for a video? So these things we would like to explore. And we believe that this approach can be extended to a cross-modality very easily because the framework is pretty much same. But we'll still like to explore that and understand the nuances in that. And we would like to thank you for being a patient listener and listening to our presentation. We hope you had a good time. For any kind of a doubt regarding this, contact us.
Now let us look at the code. For the following model, we are using the PyTorch framework, and first we are going to train the teacher model, which is a ResNet model. All the model definitions are written in the models.py file, where we have defined the ResNet model, which is a pre-trained model from the Torch Vision library, while the DenseNet and GoogleNet model architectures are loaded from the Torch Hub library, but not pre-trained. Then we have the CNN architecture, which is a 3-block convolution model, and on top of it we have the fully connected layer to give the probability whether to select a student model 1 or student model 2. Yes, the student model 1 is a DenseNet architecture and the student model 2 is a GoogleNet architecture. Now let's look at the file. Now let us look at the training of the teacher. Firstly, in the main function, we define the pre-processing steps, that is normalization and resizing of the images, and then we download the data set and load the data, and then we define our ResNet model, which we call it from the previous file that we have defined. So now from the ResNet model is then sent to the train and evaluate function. In the train and evaluate function, we train the model for given number of epochs, calculate the loss, and finally return the best accuracy model that is giving best accuracy on the validation set. This model is then saved. The saved weights are given in the Google Drive link. Now that we have obtained our teacher model and the weights for the teacher model, let us train the student model with the help of teacher using knowledge distillation. To run the file, the command that we have to use is given in the readme file. So we can pass both the model to use and the epoch as the command line argument. So in the main function, we define the transforms, download the dataset and load the dataset. We load the ResNet model, which is the teacher model here. The pre-trained model is loaded into the memory, and if we are going to train the model 1 here, DenseNet, or the model 2, which will be given as a command line argument, based on that we load the model and send it to the train and evaluate KD function. This train and evaluate function runs for the number of epochs mentioned in the function call. By default it is given the function number of epochs is 25, while we have trained it for 12 epochs. From here, for each epoch, the train KD function is called, where we get the input images and the corresponding label, and we also get the teacher's output for the given input. Then to calculate the loss between the teacher output, the original labels, we call the function lossKD, which takes the input of the current model's output, the original labels, and the softmax probabilities from the teacher model. The temperature here is we use 7. We can also modify the temperature, and we found the optimal temperature for this particular problem to be 7, and we have also tried the various other temperature values, and alpha value is also an hyperparameter. Both the temperature and alpha parameters are hyperparameters which can be tuned for better results and according to the data set. So now the loss KD function here takes the temperature as an argument and calculates the softmax probabilities by dividing by the temperature, and the hard labels is taken as a ground truth. The final loss function is calculated as the KL divergence loss between the softmax probabilities from the teachers and the softmax probability from the student, and also the cross entropy loss between the original ground truth and the generated output. By this, we are able to train the model along with the teacher's knowledge and also with respect to the ground truth, and we give the alpha value as 0.5, which is the weightage given to the hard labels. When we decrease the alpha value, the weightage given to the ground truth is reduced, and when we increase the alpha value, the weightage given to the ground truth is increased. This loss is then returned to the training function, and the loss is back propagated. Then we print the epoch loss. For the evaluation purpose, we take the validation data, pass it to this function. From here, we load each image and labels, get the outputs from the model, and compare it with teacher and the hard labels. And we print the loss and accuracy value for each epoch. After training for the specified number of epochs, we save the model. Similarly, we do it for the second student model also. Next, we look at the selector model training, where we have the create prior def function, which creates the prior, like we have two different student models, DenseNet and GoogleNet. So out of this, we have to calculate which model to use for a given particular input. For that, we are using this create prior function, which takes the input labels as the argument and two student models. The outputs from both the student models are calculated, and the absolute sum of absolute difference is found between the original ground truth and the output prediction from the both the student models. And based on this, whichever model gives the least sum of absolute difference is taken to be the winner class, and a list of all the outputs for each batch is generated and stored as a PTH file. During the training process, we will load this prior.pth file, and based on this, we train the selector model. Given the input, what class should it choose? We train the selector model based on this. And for training the selector model, we take we create the priors first, load the priors, and use the binary cross entropy loss with an Adam optimizer, and train it for 20 epochs, and the loss is calculated and been printed. After the training process, we save this selector model. Now for the inferencing part, we will look at we have outputs from student 1, student 2, and selector along with the student model. So here we are printing the accuracy for class-wise accuracy for each class and for each student, and also for the combined solution. The more first, when we get the input is passed to the selector model. The selector model will decide whether to select student 1 or student 2 for the given input. Based on the output from the selector model, we pass the inputs then to the student 1 model or the student model. The final predictions from student 1 or the student 2 is taken and used to calculate the loss or for the inferencing purpose.